We present CAFE-MPC, a Cascaded-Fidelity MPC framework with tuning-free whole-body control. This framework enables on-the-fly synthesis of highly dynamic yet complex motions on quadruped robots, such as a running barrel roll with various locomotion skills. CAFE-MPC employs a high-fidelity plan in the near term of the prediction horizon and a low-fidelity plan in the distant term. The high-fidelity plan attempts to accurately represent the real problem. This is done by reasoning about the whole-body dynamics, employing a fine integration time step, and enforcing all possible physical constraints. By contrast, the low-fidelity plan purposely relaxes some accuracy with the aim of gaining computational efficiency. As such, the low-fidelity plan reasons about a simplified template model, in this case a single rigid body model, employs a coarse integration time step, and uses relaxed constraints. The high-fidelity plan and the low-fidelity plan are connected serially in time via a transition constraint. To summarize, CAFE-MPC relaxes the optimization problem of MPC along the prediction horizon, with the motivation that details in the future are less important to affect the current decisions than that in the near term. The model schedule of CAFE-MPC represents the horizons of each plan and can affect the tracking performance of CAFE-MPC and the solve time at each control tick. Here we fix the length of the whole body plan to 0.25 seconds and vary the SRB plan from 0 to 0.3 seconds and demonstrate the effect of the model schedule with a trotting gait on the MIT Mini Cheetah. With short SRB plan, the controller attained bad tracking performance. As a result, the robot gradually drifted and fell. The tracking performance is significantly improved as the longer SRB plans are employed. Moreover, growing the SRB plan appropriately does not necessarily increase the average solve time per iteration. This is because with the longer prediction horizon, the local feedback policy may have a larger region of attraction, resulting in more aggressive step sizes for the line search. Conventional whole-body MPC produces a whole-body plan that is directly executable on the robot. In practice, however, a local Riccati feedback controller that runs at a much higher loop frequency is needed to achieve higher control bandwidth. The disadvantage of this approach is that the output of the Riccati feedback controller does not necessarily satisfy the constraints in the whole-body MPC. Conventional template MPC produces a low-dimensional plan often in the task space. A low-level whole-body controller, for instance, whole-body QP, is often employed to convert the plan to whole-body commands. The disadvantage of this approach, however, is that the template MPC is not aware of the whole-body constraints and that non-trivial tuning of the QP is often needed. Similar to whole-body MPC, the CAFE-MPC entails a whole-body plan in the near term. Nevertheless, instead of using the Riccati controller, we propose to use a value function-based whole-body controller, for short VWBC. The VWBC embeds the Riccati controller within a whole-body QP, allowing the use of the same set of constraints as in CAFE-MPC. A Q-value function is used as the objective for VWBC. The Q-value function measures the effect of the current decision on the long-term tracking performance and is obtained from the CAFE-MPC, thus avoiding additional tuning. We compare the Riccati controller and the VWBC on their performance of dealing with the friction constraints. The robot is commanded to execute a bounding gait at 1.0 meter per second in simulation and is pushed with a disturbance that creates a 1.5 meter per second change in the forward velocity. The robot controlled with the Riccati controller slipped and fell, whereas the robot controlled with VWBC satisfied the friction constraints and recovered from the push disturbance. We now showcase the capability of the proposed CAFE-MPC and VWBC framework on several highly dynamic motions. Dynamic running jump. The robot runs up to 1.5 meters per second and seamlessly jumps over an obstacle of 20 centimeters width and 10 centimeters height. Several extremely dynamic barrel roll motions. We compare the CAFE-MPC with a conventional SRB-based template MPC in terms of performing an in-place barrel roll in simulation. The robot controlled with the template MPC failed to complete the barrel roll due to the reduced body angular momentum. This is because the body angular momentum and the leg momentum are not coordinated in the template MPC. The CAFE-MPC achieved success, indicating the importance of incorporating the whole body dynamics for such highly dynamic motions. For the in-place barrel roll, we generate the barrel roll reference using trajectory optimization offline and connect the in-place trotting reference to it. The same in-place barrel roll reference is then used with a trotting reference and a pacing reference to synthesize a running barrel roll with the associated gaits. The proposed control framework is capable of executing these motions on hardware even though the barrel roll reference is designed for the in-place taking off. We further commanded the robot to perform a running barrel roll without the intermediate stance phase before taking off. We emphasize again that the same in-place barrel roll reference is used here. We repeated this experiment for 22 times to examine the reliability of the control framework and achieved a success rate about 70%. 8 successful experiments are shown here. Lastly, we pushed the robot very hard to show its disturbance rejection capability on the hardware. In response to the push disturbance, the robot not only placed its stance feet toward the direction of disturbance, but also lifted its swing legs to the opposite direction, which attempted to reorient the body by regulating the angular momentum. This type of reaction is only possible when considering a whole body model and planning. The remainder of this video entails some failed experiments. The robot shut down due to the loss of Ethernet connection. Insufficient angular velocity at takeoff due to low battery. The robot slipped at taking off.